Welcome. So let's talk about our second video of this week. Specifically, we're going to change chapters. So we're going to move on from induction and we're going to get into ordered pairs, almost multivariable kind of world. So you've dealt with ordered pairs before, and they're anything of the form X, Y, where the order matters. So, and two ordered pairs are equal if and only if the components or coordinates or their corresponding terms are equivalent. So we then up this, we call this an n tuple. You may have, sometimes this is called a vector, where we're just talking about x sub I being the ith component. Now, real quickly, if you want to call this a vector versus an n tuple, I'm not going to get on your case. I once mentioned this in a mathematical meeting, and someone in the crowd thought that I called it a vector and they didn't like it, so they wanted me to call it n tuple, whatever. It's really the same object. It's just a ordered list. We can have the same thing repeated as many times as we want. We have indexing and so forth. Now, one of the key things to understand for definitions is something called the Cartesian product. If you have two sets X and Y, the Cartesian product is an ordered pair. Now, notice Cartesian product uses the multiplication symbol of X. And the Cartesian product then is where I simply pick the first coordinate has come from the first set, second coordinate for second set. That means that X, Y, and YX are going to be a little bit different. It's kind of important. Sometimes we go X cross X to be X squared. This, by the way, is more common, especially when you see things in the notation of, R squared, which is really R cross R. So it's two-dimensional space. Or you can raise it as many times as you want. This is the pi thing, meaning I can do this of n sets and get a n tuple. So we're essentially giving ourselves the domain and so forth. So we're just going to start off playing around with this a little bit. Let me start you off with an example. So here, A and B are 1, 2, 3, and this funky symbol square. That means that A cross B is 1 with the red baron cross, 2 cross, 3 cross, 1 star. Now you could have written this because this is a set, the ordering doesn't matter. It could have 1 cross 1 square, 2 cross 2 square, and so forth. My question is, what is B cross A? Now that answer is actually the same exact thing, just switch all of those orders. So instead of writing it down, I'm going to do a plus cross 1, plus cross 2, plus cross 3, square cross 1, square cross 2, square 2, and square 3. So notice I have the exact same number of things. They look very much alike. They're just a little bit off because the ordering matters. What about B cross B? It, on the other hand, will have a few options. Namely, it will have plus, plus, plus square, it will have square plus, and square square. And we can kind of see from this kind of a pattern about the number of elements in here, but I'm not going to reveal it because I'm going to let you all figure that out explicitly. Namely, what can we say about the X cross Y versus Y cross X? And I love this second question. When are they exactly equal? It's kind of an important note. So I'm going to have everyone work on these problems because there's not a lot of them. Then the next one is if they're both finite sets, so they're not infinite number, how many elements are in the Cartesian product? And I want you to be as specific as possible, not be like a lot. But let's say that you can, if you give a number to X and Y in terms of the number of their cardinalities, what would be X, the cardinality of X cross Y? And last but not least, I want you to find the Cartesian product of A, B, and C here. So these are going to be ordered triples, mind you. All right. Keep that in mind. I think you all got this one. should feel pretty familiar, but we're going to take this up a notch in just a little bit. Good luck.